as well as YouTube. So I want to check the participant in YouTube and Zoom. Are you getting the signal? Are you getting the able to get the voice from us? Get any? So first time we are linking it from the Anna Centenary library. So we are using an external device, not the internal device. Just we want to check. So is it audible to them? Okay. Yeah, it's okay. Zoom is YouTube is linked through Zoom. Okay. On behalf of Tamil Nadu Science Forum and PSL, I'm extending warm welcome to you all. This is our 52nd lecture. So we are coming back to the hall after 18th lectures. First 18 lectures were held in halls, and later due to COVID we are going for online meeting. Now we are coming back to this one. This is going to be a hybrid meeting. People is attending from different part of India because during the COVID period, the PSL has been extended to entire India, and people from different part of the country are attending. So now this is the 52nd lecture, and the topic is the quantum entanglement. So I invite Professor T.R. Govindarajan to initiate the meeting, and we'll have the meeting will be moderated by Dr. H.S. Mani, and the speaker is Dr. Shibashis.
Okay, thank you very much. And I'm very happy that this program now, which was always held online for the past 2 years, we could restart. Well, this restarting of this personal lecture helps particularly students from Chennai, okay, quite a bit. I know I've been to MCC, I've been to Vivekananda, Loyola, Vaishnava College, several colleges, and I'm very happy that the students from many of these places have come for this program, particularly those students who are interested to know about this thing. So that is the first part of the thing. Tamil Nadu Science Forum has been functioning for the past 40 years. It has been focusing on issues in relation to primary classes, elementary classes, middle levels, and school level. And this popular science lecture is focused on more than school, okay, more than school. And we want to reach the students who may not have the links like many of us. I myself, I worked in Institute of Mathematical Sciences, I worked in Madras University and IIT, etc. So we have some links. So people there come and give lectures. So there is some thing which is, but it may not be always happening in colleges, and particularly you find it better to talk to the people who are actually doing the work. That is the focus of this thing. And we are trying to popularize in the sense of that there is some excitement about science. Okay, it might be physics, it might be chemistry, it might be medicine, it might be biology, or it might be climate change, or even rational thoughts, okay, rational questions, etc. And we have been getting people to talk about all these issues. In fact, COVID has provided so many chances for us to talk about epidemiology and what is actually COVID, what is that virus, and how people were doing the work, etc. So this is the way in which we have been focusing on. And I will not spend too much time because we never want to spend time on irrelevant issues, gaga and whole thing which we do, but we will directly go to the meat of the matter, which is going to be today's program and next 2 days program, next two programs which are there. So I will introduce those two things and the speakers. So the program is, every year around this time in October, first week, the Nobel Prizes are announced. We have been having meetings to talk about the Nobel Prizes. What is it actually they have given and what exactly they have done the work for. Okay, that is the idea. So that people become interested to know about why is it being talked about. So today it is going to be, this was held last year, but it was online. But the year before it was held in Madras University and other places in 2019 or so. 2020 and 21 we held in online meetings. That is the way it was held. But 2022 we are having it here in this hall. And in fact, today's talk, as you know, um, this issue of physics Nobel Prize, because it's also my area where I have some interest and expertise. So this is about how the information is communicated, okay? How information goes from one place to another place in a quantum world, okay? So it has become very, very important that can you communicate information without anything in between? Can you communicate with somebody in Andromeda? Can you communicate something in other places without anything intervening? Okay? So this issue of quantum entanglement is exciting from science fiction kind of issues, but at the same time, experimentally what can be done? How far? Even if you achieve that there is something disturbance here and another 1 feet away, but there is nothing to tell you that it has traveled all these things, is very, very important. Okay? So that is the idea about quantum entanglement, and that is, we have been always talking, these people mentioned here will get the Nobel Prize, but every year they have been missing it, but this time it has been given, the 3 people, and we are going to celebrate that by giving exactly what is the issue and what has been, what is it these 3 people have achieved. Okay, that is the idea. The next is about the medicine, which will be held next week, Saturday, again by hybrid meeting, next Saturday, the same place it will be held, and following that about chemistry 1 week later. Okay, the 3 weeks are specially designed for Nobel Prizes in physics, medicine, and chemistry issues. So we are happy that many of the students, and not only students, even people who are interested in science, have come from several places, and I am also happy that many of them are attending through Zoom, okay, Zoom and YouTube, and they will also ask questions. We have a vibrant question and answer session towards the end. After the talks are over, you can ask the questions, and to the extent we have to cut off at some stage, maybe around 5:30 or 6, we have to say enough. So this is basically the idea which will be done. Now, there are 2 people who are going to speak today. One is Professor H.S. Mani, he's here, and he will introduce why is it this topic is interesting. Okay, why is it we are excited about it? Why is it this Nobel Prize has been given this year? Okay, and the background for this thing he will introduce, and he will also moderate the today's program. Professor H.S. Mani, he is actually a 40-year friendship with me, because when I was a student in Madras University, he was a faculty in IIT Kanpur, and then I went to IIT, and he was a professor there, and he became later director of Harishchandra Research Institute, HRI, there in Allahabad. Now it is called Prayagraj. Okay, so that is the place thing. He was there. After that, he has been in S.N. Bose Institute in Calcutta, and later he moved to Chennai. He's a Madrasi, so he has been here associated with Chennai Mathematical Institute. Like me, who was associated with the Institute of Mathematical Sciences, we have been talking and discussing several things. Professor H.S. Mani works on high energy physics, and that is his expertise. So he has been of late following various things, issues in quantum mechanics itself, and he is a great teacher. The greatest thing about him is his teacher, as a teacher, is regarded as a great teacher in IIT Kanpur, where he worked long time, and also in many other places. So that is Professor H.S. Mani. The next is Professor Subhashish Ghosh, who was my colleague in Institute of Mathematical Sciences. He works on quantum information theory, or these issues about foundations of quantum mechanics to some extent. And he is a person who is actually working in many of these questions, theoretical works he has been doing, and he has been in touch with several other institutions outside, as well as he is a well-regarded physicist who is, in my opinion, in Madras, there are only few people who can talk about these kind of thing in nitty-gritty details, and he is one of them. So I'm very happy Sebastis has agreed to speak, and Professor H.S. Mani to take initiative to talk about this. So I'm going to cut down my talk, and I will leave it to Professor H.S. Mani to introduce, following which Sebastis Ghosh will follow with what he is to do. Okay, thank you.
Thank you, TRG. Good evening to you all. Firstly, I would like to thank T.R. Govindarajan, Vijayan, and his crew for doing such a wonderful program here. It is really remarkable that you people are doing it. I think we have to appreciate that a great deal. Now, regarding today's talk, I will just give you an introduction and whet your appetite for the situation we are in terms of quantum mechanics. It is actually a very confused state of affairs as far as many ideas are concerned. It conflicts with us, with our normal way of thinking. The example I like to quote, or there are several. In the development of physics, when concept of something like force, it took more than 150, 200 years to realize that what we teach physics force in the high school. Similarly, the concept of heat, which we think of as a form of energy, it also took 2 decades. Now we are in a similar threshold in quantum mechanics, and this is the main aim we would like to emphasize. Do you agree with me? Okay. So given that, I would just like to give you an introduction to somewhat to Professor Ghosh's presentation. So I will just start with this. The Nobel Prize was given to Alain Aspect and John Clauser and Anton Seilinger. Quantum mechanics, as I have mentioned just now, our understanding of nature, just like the understanding of heat, changed when we understood it in the form of mechanical energy, or it is another form of energy. This change is taking place. The work of Alain Aspect and John Clauser has actually demonstrated this experimentally. How do I do this? Or am I to keep it this way? அல்லது நீங்களே பண்ணிடுறதா? நான் சொல்லிடுறேன். Okay. Now you could go to the next slide, please. Yeah, this is the kind of broad apparatus that was used by Clauser and Aspect. There in the middle, there is a source which emits photons in 2 different directions, opposite direction, and the photons are characterized by what we call the polarization. They can have different kinds of polarization. They can be set up again from one polarization to another by using certain optical devices, and then you measure a correlation between the polarization of the photon to the left and the correlation between photon to the right. They will of course carry the information when they left the source, but the way the information is categorized in classical physics is very different from quantum mechanics. This is the point which will be emphasized later by Professor Ghosh in great length. And when the experiments were performed, they led to certain relations, and they are put in terms of some inequalities. Some number, if it is classical, must be less than 2. But experimentally, that is not true. That number, when actually experiments were carried out, was much greater than 2. This is what is called the violation of the Bell's inequality. Bell is the first person who established such inequalities. Before that, people were just generally discussing things, but Bell brought it in the front of an experiment to show the classical thinking will not always match the quantum thinking. Next slide, sir. And this requires, as Professor Govindarajan has mentioned, the idea of entanglement. they use this entangled state. The source which I showed in the previous slide had those entangled states. Then Zeilinger used these entangled states also to do what Professor Govindarajan said, to teleport a state from one place to another. Here I would like to explain a little bit. It is classically also I can teleport a thing. It is I take a sheet of paper, I take it, put it in a photocopy, and I can send it to IMSC to picked up by somebody. So I'm teleporting it from here to there. And you give me another sheet of paper, I can do that. In quantum mechanics, you cannot do that. If I put one paper, the machine has to be specifically arranged for that copying to be done for that paper. And once that is done, that machine is useless as far as further copying is concerned. Yeah, if I have to copy another paper, I have to hunt for another machine and then do this process. Very different from the classical situation. So this is something, yes, A will be able to teleport something to B, but what A had is gone. Now it has to be replaced by, again, another source has to be replaced before he can do that. That's the difference. And now B will make an appropriate transformation to get the state. This leads to the development of quantum computers and quantum cryptography. This is the clues where a person, when he tries to disturb the system to look at it, this information would have reached the parties which are sending the thing, and how efficiently you should do. And the other side would like to see how efficiently he can see doesn't disturb the system are part of the game that's being played in the last 2 decades or 3 decades. Please, the next slide. It's working now? All right. Now I will give you a mind-boggling example of what is called the quantum pigeonhole principle. This is really mind-boggling. Supposing I have 2 holes and 3 pigeons living in 2 holes. Ordinary thinking would tell you that one of the holes must have 2 pigeons. Quantum mechanics, this is not true. I can make a measurement for 2 pigeons in hole 1, I will not find it. I can make a measurement for finding it in hole 2, you will not find it. There are such states and such measurements, and those of you who are interested in understanding this more, I can give you the papers and help you work it out to understand how the basic ideas are. So you can see how different quantum mechanics is from classical mechanics. The quantum pigeonhole principle is just not there. Okay. Now, next thing, having told you how different it is, and we have to understand all this properly, we need some mathematical apparatus. And here, I will like to discuss a 2-dimensional vector space to understand the work of the Nobel Prize winners. I will talk, normally one would have talked in terms of bits takes 0 and 1. All bits in our computer and take 0 and 1, there are 2 states. Quantum bits have a much bigger space to operate. Instead of talking in terms of quantum bits, I'm going to talk in terms of something which undergraduate physics people know is in the form of light which is traveling, the polarization vectors. And anyway, the experiment done by Clauser and Zeilinger were using photons. Now, the way, if I have a wave which is traveling, say, in this direction, the electric light is a form of electromagnetic wave. So I have electric field in a direction perpendicular to the motion of the wave, and magnetic field is in that direction. So electric field to magnetic field, if I do, it will move that way. At any given place, the electric field vary like this. It has to keep varying. That variation is what produces the magnetic field, and they help each other in doing this. That's how the electromagnetic wave proceeds. So the wave is transverse. The electric field, supposing the electromagnetic wave is along the z direction, the electric field will be along the in the xy plane. They are also mutually perpendicular. So E, B, and K, they form a right-handed coordinate system. E, B, and K form a right-handed coordinate system. Oh. Pardon? All right.
This is Entangled.
Yeah? Pardon?
This one is Entangled.
Oh. That was next slide. This is the way I have depicted an animation. And again, I must thank Ritesh Bharat. Is he here today? He is the person who helped me with all this. He did all this from Pondicherry and did all this work for me. Yeah. Next slide, please. I have here a polarization. It can be, the polarization can be along x-axis or y-axis, which I have written as Ex times a unit vector along x-axis, and that is Ex I cap, and another unit vector along y-axis. And I will assume here is where a little bit of mathematics comes. The oscillation which I write down is in terms of the following formula, which I have written to the right-hand side. Can I show that? Is there a light I can lay the beam? Okay. No, it went back. No.
You have to you're pointing it towards the computer.
Oh, I have to do it this way? Yeah, I thought that's right. That's right. I have gone forward. No, here it is. This formula is the what I use, e to the minus I theta. Cosine theta is a sinusoid, it varies, oscillates like that, so does sine. So these are the equations which I have, which we learn actually in trigonometry in school, but if you're in biology or medicine, you might not remember it. But the main idea is that there is oscillation which takes place. Here is how it goes. This is one kind of possible polarization. These are called linear polarization. Here is another way. You could also do it in a third way, which will be a combination of these two, and that is called a circular polarized light. One could be left circularly polarized, another one right circularly polarized. This is the right circularly polarized which I am showing here, and the details of how this happens are worked out here. I will not go over all the details. Those of you who are interested can always talk and find out. Next is here, I have redrawn this. Notice at any given point, the light, oh my God, no, I have gone forward. Here it is. Now notice it is going anti-clockwise and the beam is going forward. This is left circular. If it is clockwise, then it is right circular. Now, these things can be written in terms of a column, what is called the matrix. Right circular I write is EH, EY. Left I write EXI. I is square root of minus 1. I can combine this and write EX in terms of these two. These are the mathematical things which Professor Ghosh may need, and so I have written it in this form, EX. Notice I can write down in terms of linear polarization as a combination of right, left and right. Here it's a minus I, here is a plus I. So I can write down all these possibilities, and experimentally you can produce all of these possibilities separately. Okay, here it is. Here is the linear polarization, and I have broken it up into two. One left circularly polarized, another one right circularly polarized. These two add up to this. Okay, the same thing has been redone and rewritten in the following form. Here is a vector in the x direction moving like that. Here is a vector which is, all these are about electric field of the light opening. And here, this is the right which is clockwise, and this is anti-clockwise. And there are several other possibilities. I will just deal with these now. Others are very similar. Okay. There is another geometric interpretation of a two-level quantum system. These are for whatever the states we have been discussing, and they are called the pure states. The most general two-level system can be represented by an expression like this. There are two. This is just an overall phase, and I don't need that. I only use these two ones, and this is polar coordinates. Notice here, this is my x-axis, this is my y-axis, and that's my z-axis. And this polar coordinates which we use are r, the length is 1, and this angle is theta with respect to the z axis. This is the state, quantum state here. Psi is the quantum state. So psi here. It's the same state. And now here this angle is phi. The azimuthal angle, which is here, which can go to 2 pi. Theta can go from 0 to pi. So now if I take theta equal to 0, then I will just have a state right here that will be 1, 0. Every point on the surface of the sphere is a state. So I have 0. Let me go here. This corresponds to theta equal to pi. When I put theta equal to pi, cos pi by 2 is 0, sin pi by 2 is 1. So it is this state. Similarly, I can write down states here. These are circularly polarized states. All the ones on the equator are circularly polarized. So in between I can have many states, and this is a way in which a pure state can be represented on a sphere. This is a geometrical representation of a quantum system. Now, next important concept, which I have already talked about at quite a bit, is about the measurement in classical physics. In classical physics, measurement means a property exists predetermined and it was observed by a measuring device. Example, take a temperature of a body. If I take this water bottle, I assume that its temperature is known. I have to only measure it. How will I measure it? I will insert a thermometer, and the heat capacity of the thermometer should be much less than the heat capacity of the water in the bottle, so that there is no change of the temperature of the water bottle. And if I make the heat capacity go to small, the temperature changes of the water bottle will be negligible. So I can measure the temperature of the water bottle without disturbing its temperature in the limit. In quantum mechanics, this is not necessarily so. Now again, I could manage. Quantum mechanics, why is this there? Okay. Here it is. It need not have a predetermined value. It could be a combination of different values available to it. After measurement gets performed, an outcome is obtained. The system gets disturbed and it comes to a new state. That state collapses. In general, it is not possible in quantum mechanics to make a measurement without disturbing the system. And this is what leads to the famous Heisenberg uncertainty principle and leads to here. Here are two things which are written. The position in space, if I am putting the moment, this is the wave function measurement, and if I make a measurement, the system will collapse to a state like that. But in general, it was a system of that nature. Now, the actual experiment which produced the two photons in the experiment of Clauser, I am just giving you some details here. And there is a purpose I am giving it, I will mention that to you. What happens is, there is a laser beam which comes and it interacts with the crystal and produces two beams. And the two beams come out in the form of cones. One cone upper and one cone below. And where they meet, where the cones meet here and here, the photons which are coming in there, two photons are coming with lower energy than the original beam. Original beam had, say, some 2 MeV, 2 electron volt. This could be 1 electron and 1 electron volt. And one of them will come in on a cone, the other one will come here. That will depend upon the crystal structure of the crystal. We are not interested in those details. But they will meet. If they meet, at the place where the photons are coming, they are entangled. These are entangled photons. This is how entangled photons are produced. And the kind of things we had are these KDP crystals, which are called breakdown or spontaneous parametric down, right? Right, down conversion, correct. So now the point is, in India also, several such experiments should be done, and it was about, say, 10 years ago, I was also interested in seeing some undergraduate experiments can be done. American Journal of Physics, which is the place to look for, you see several such undergraduate experiments done all over United States and England. So why should we not be doing it? So I got into touch with persons who are doing experimental work in Raman Research Institute, IIT Kanpur, Anant Ramakrishnan, And Anantharamakrishnan, being an old friend of mine, I talked to him more, and he said these are all very expensive crystals. All these are photons which have very little intensity. You can't use 10,000 photons. So you need one photon, and then you need detectors which can measure such low intensity. So this kind of a work is very, very difficult and very challenging. But again, unless we do this kind of work, we will be left behind like what we have always been left behind. So this is a challenge for all of us to see what are the kind of experiments we can go and do it in an undergraduate lab. Maybe some of them are not very easy. Quantum erasure is one possibility, and there are several such possibilities which will explain the basics of quantum mechanics. Instead of just going on measuring using Fourier thing about heat conduction and so on, which is about 200 years old, and we can just try to do. That's one of the reasons why I put up this slide. And okay, using all this, there was an inequality established, derived by these relations were in the form, I've already mentioned that, if they had obeyed classical physics. As per Clauser and co-workers experimentally found that two correlated photons, that these inequalities are not satisfied by a large margin. The main assumption in deriving these inequalities, they are classically correlated. The exact mathematics of it is a little involved, but it's not all that difficult. It can be understood by an undergraduate student without difficulty. This implies certain possibilities can be assigned to different choices of measurement. This forces us these inequalities. And here is the actual apparatus which was used. Light comes here, is your spontaneous down conversion, the two photons coming, and these are focusing the photons. These are halfway plate A and B, and these are beam splitters taking it to detectors, and they take to 4 different detectors. One on this side of the photon, the other side of the photon. And these are the correlations which are done. And one should also ensure that there is no communication from here to here, and that again is a very interesting technical method of doing it by having these things work at very, very rapid frequencies so that the photon here cannot interact with the photon there. This is the broad picture. And the measurement uses the entangled states all the time. And this is, of course, I've mentioned again and again. Perhaps one can extract work from the measurements. And here, I must say, Professor Ghosh has a very nice paper on how using measurement, one can use it as a Carnot cycle and measure, get an energy output. And here is the famous Schrodinger cat, radioactive substance hitting a liver, and the liver collapses and some kind of a poison or whatever is emitted, and the cat is living, and instead of the standard thing, I'm going to say it is sleeping. And so it is a mixture of states, which is a combined state of a living state and a awake state and a sleeping state. But these are the kind of questions which have to be answered when it comes to macromolecules. How can you do this? Is the question. I thank you, and I will now request Professor Ghosh.
Okay. Thank you, Professor Mani. It's a very difficult task. Okay. Well, I actually requested him to minimize the mathematics, and he did make definitely great effort. And there is some mathematics is needed. We cannot avoid it. But what was the mathematics used was only what is done in two-dimensional physics, like x-axis, y-axis, vectors like that. So it's going to be that kind of a thing. Now, Professor Ghosh will continue and try to tell you precisely what was done by Alan Aspect, John Clauser, and Zeilinger, for whom the Nobel Prize has been given. Okay? Now, Professor Ghosh.
Okay. Thank you, Professor Tiaji, and thank you all to be here to attend this Nobel Prize 2022 in Physics lecture. I must thank Professor H.S. Mani to make my life much easier, because otherwise, within the short span of time, it will be much difficult for me to explain all these things. Okay. So, I'll do this. So this is, so my topic, so the title of this talk is Quantum Entanglement. So the Nobel Prize has been given on entanglement, is experimental verification and usage. So let me try to take you into a little bit deep of what entanglement means, what can I do with that, and what about the experimental verifications of entanglement and related issues. So before doing that, let me try to introduce this notion of indeterminism. Professor Mani introduced this notion of indeterminism of measurement outcome in quantum mechanics. Let me try to introduce it once again to just compare the situation with the classical world. When I say classical world, it means the world where we live, our surroundings, where the laws of classical physics will hold good. Namely, Newtonian mechanics, classical thermodynamics, then classical optics, all these things will basically, it will hold. Okay. So the question is there indeterminism in measurement in classical world? One might say, yes, why not? If I
He wants to change it.
Okay. So let us go through this example of coin tossing. Everybody here knows what a coin tossing means. Whenever we get to see cricket match, football match, etc., who will start batting, etc., that is decided by the result of coin tossing. So if I do coin tossing,
No, previous.
next page. That's it. Yeah. So this coin tossing, you say that when I toss a coin, I'll have either head or tail. Okay? When I get to see what result is coming out, it will be either head or tail. Question is, can I say a priori, before doing this coin tossing experiment, what will be the outcome, head or tail? If I can do that, then that will be the idea of determinism. Okay? So I can do it deterministically, tell deterministically. Okay? So the answer in the classical world is yes, we can actually tell what will be the outcome of a coin tossing, provided we know what force we have applied, what velocity or speed was the initial velocity or speed of the coin, what was the reaction or interaction of the coin with the air, that means air resistance, what was the reaction when it falls on the ground. If we know all these issues, then we can figure out, without doing this coin tossing experiment, what will be the outcome, exactly the outcome. So in other words, in classical world, there is no indeterminism in principle. Even though, there are events where we don't know what is going to happen. For example, whether I'll be alive next 1 month or so, I cannot tell. Okay, so these kind of issues are there. But in every physical phenomena, what we get to see around us is deterministic in principle. It is our subjective ignorance that we can't tell a priori what will be the outcome. Okay? So in classical world, there is in principle no indeterminism. Everything is deterministic. Okay. So that is about coin tossing. Now one might say, okay, how do I know that if I am or some material here is correlated with something else, some event is correlated with something else which is far apart, and if I do some measurement on my system, how this correlation is going to be affected, and on the other hand, how this correlation is going to affect my measurement result. Like, if I walk on floor, unless there is a friction, I will fall. Okay? So this frictional force I'll have to take into account to justify why I am not falling every time. Okay? So that's a kind of correlation. When I look at prices of goods in market, like whatever we take for our food, etc., like lentils or paddy, whatever, then we'll have to see what is the price of the petrol or diesel, etc. Because, that price will be, increase in the price in petrol or diesel will also affect the price of goods. Okay? So there is this kind of correlations are there. Okay. So the question is that if there is material correlation, like I have two balls, material balls, which are connected with a spring, and let us keep it on this table. So if I move one ball, the other ball will also move. If I move it fast, the other ball will also move fast. Okay? So there is a material connection. So you can say these two balls are connected, correlated. Their motions are correlated. On the other hand, we can have correlations without such a material connection, like yields in paddy field. Okay? That will depend upon the rainfall in a region. Okay? So there is no direct material connection, but the correlation is there, connection is there. So if there is huge amount of rainfall, there may be, it is going to affect the amount of, yields in the paddy field. Okay? So these are kind of correlation we are associated with in our day-to-day life. Okay. So the question is, when things are correlated, two things or more than two things are correlated, and when I want to look at certain property of one particular thing, one subset of that, is it still true that the event, let's say I take these two masses associated with this spring. If I move this mass, of course this mass will also move. But the question is that, can I say that the movement of this mass is completely deterministic? Okay? In the sense that, even if there is, some correlation, still it is deterministic. So, in everyday life, we have some deterministic events, like sun will rise on the east every day. There is no change in that. But there are also issues which are probabilistic in nature, statistical in nature. And it is these events which are statistical in nature that create some problem in justifying whether the event associated with the statistical nature is deterministic or not. Okay? So here also, as I said, that in the case of one mass, two masses connected with the spring, even movement of one mass is determined. One can make it deterministic. It's not a problem by knowing everything. Similarly, in the case of, let's say, second mass also, it is the same. So the thing is that when I talk about correlation, one might say that, look, I have two masses, they are connected with spring, I move this mass, the other mass will also move. If I move it faster, it will also move faster. If I pull it there faster, it will go on this side. Okay? So this kind of correlation is there. Question is that, can I, when they are correlated, or even when they are not correlated, can I determine the displacement of this mass or the speed of this mass together at a time? Like, you have a moving car. Can I figure out what is the speed of this car at a time, and as well as how much it has moved? That means the displacement. Can I do it simultaneously? Yes. In classical world we can do. There is no harm in it, even if it is correlated with something else. Okay? Right. So we'll see that all these notions, this determinism, and then simultaneous sharp values of measurable quantities are not the case in quantum. Okay. So, two notions which are very, very fundamental in order to understand why Nobel Prize has been given this year on these entanglement and related issues. So these two notions are very, very important. One is the idea of locality. So, this locality is that, let's say I talk about again these two masses, two balls connected with spring. If I move this mass here, I know this will move, but it is not instantaneous. So it will take some time for the second mass to have movement. Okay? For example, I take a magnet, a bar magnet or whatsoever on this table, and put some, some iron here, iron body, maybe some nails. If I bring the magnet towards this iron, these nails will be attracted, but it will take time. However small it will take time. So what I want to say is that this influence, that means whether I am disturbing it, moving it, etc., this influence in classical world cannot happen instantaneously. It will take some time. And what we know from physics background, that no information, physical information, can have speed much, greater than the speed of light. So there is a finite speed of any information that can, any influence that can. This is true in classical world. It should be true in quantum also. Right. So the locality principle tells you that when I do something here on my system, the outcome of this doing something, that means outcome of this observation or measurement, is not going to have influence the other system instantaneously. Okay, so that is the notion of locality. And all of us, we agree that yes, our classical world should have this property. The other one is this notion of determinism, which I introduced, initially, that in classical world every event is in principle determinism. Okay? And so it tells you that the results of each measurement or observation process can be predicted with certainty in principle. Overcoming the subjective ignorance that I told you. That means I don't know the force, etc., etc. Therefore, I can't tell you, beforehand. If I know all this, I can tell you. So, the important thing which Professor Mani alluded to is that whenever I perform measurement, what is the speed of this vehicle, what is the length of this table, etc., it will reveal, the measurement, if I do it properly, it will reveal only those values. Like if this table is, let's say, 1 meter length, it cannot reveal, if I do it properly, the measurement, it cannot tell you that its length is half meter. Okay? It cannot tell you. So, proper measurement, if I do it intelligently and properly, will only reveal the values of those observable quantities, nothing else. Okay? So, this locality and determinism are the two basic ingredients of whatever physical world we get to see. Around us. The classical physics, whatever physics we get to see, these two notions, reality and locality. Our reality is also called as determinism. So determinism and locality are two basic principles of the classical physics that we are aware of. You can forget about any other property of classical physics, okay, for our discussion. Just these two principles we will talk about. Okay, good. The next notion, now, okay, so before going into that, so it was Albert Einstein. Albert Einstein got, he did works in physics, which changed our worldview. There is no doubt. Before Einstein, the world we used to perceive is one. After Einstein's work, it is something else. Okay. But Einstein was a strong proponent of determinism in our world. So he used to say that, look, God doesn't play dice. Okay? So whatever happens in our world, classical world around us, it should be deterministic in principle. If I cannot tell you, he will tell you. If I and you cannot tell you, somebody else can tell you. Okay? The outcome of measurement deterministic. And it is this notion of Einstein which he carried out throughout his entire life. Okay? So, now, point is that Now, in science, I cannot just say that I am a believer in determinism or I am not a believer in determinism. If I say that, it doesn't make much sense. So it should be context dependent. Okay. So what Einstein did to make our life means the physicist working in the later years difficult, is that he wanted to convince that look, quantum theory that we people are talking about, it is correct because it can provide results which are incommensurate, which are commensurate with or compatible with the experimental result, no doubt of it, but it is incomplete. So what is the notion of completeness that Einstein used? So according to Einstein, a complete physical theory, that means theory of nature, maybe classical physics, quantum physics, whatsoever, or some other candidate, it must possess the allowed values of all its observable quantities, be it position, momentum, energy, etc., etc. Okay. And whenever I perform measurement, it must reveal only these values and nothing else. Okay. And it doesn't matter which observable quantities or how many observable quantities I am going to measure together. It doesn't matter. Okay. So that was the notion of completeness which Einstein used. Okay. So as I said, if I have a moving car, I can figure out its speed, how much distance is crossed, what is the mechanical energy, everything I can figure out in one stroke. Okay. So the question is that Einstein, when quantum theory disturbed him so much that for a single quantum system, let me say maybe an electron, maybe a photon or whatsoever, so he wanted to tell that look, when I perform measurement on a single quantum system, like if I have a photon, I want to measure what is its polarization. Is it horizontally polarized or vertically polarized? Whenever you have a spin, I want to figure out whether its spin is along a positive z direction or negative z direction, etc. Quantum mechanics tells you that no, you cannot tell with certainty. There will be some probability of getting up z spin or down z spin. There will be some probability of getting horizontal polarization or vertical polarization. So that is what I mentioned initially, that this indeterminism is kind of inherent in quantum mechanics, which Einstein was completely against. So what he did is, so for a single system to say that look, there must be some underlying theory, our subjective ignorance is there, therefore I cannot predict with certainty what will be the measurement outcome in quantum world. The point is we cannot, neither we can contradict you nor we can support you, unless we specify further properties. So what Einstein did is that he introduced a bipartite system, what Professor Mani told, a system of two photons polarization, or a system of two spin-half particles together. And that, using that, he wanted to prove that quantum theory is incomplete. Okay, so existence of this incompatible set of observables of any single quantum system does not allow to have sharp values. Sharp values means what is, I said, exact length of the table or whatsoever. As measurement of one observable, so as Professor Mani said, in quantum theory, in quantum world, if I perform measurement of some observable quantity, like position or momentum or whatever, or spin, it is going to disturb the state of the system. Therefore, if I want to measure some other observable, I will not get the exact desired. Unlike in the classical world. Classical world, I can, in principle, perform measurement without disturbing the state. So, I can measure the speed of a moving car without disturbing its motion. In principle, I can. Okay. So, what Einstein did is, using a correlated state of a composite quantum system consisting of two subsystems and inferring the sharp values of simultaneous measurements of two incompatible observables. So, what he did is he took these two systems, he did something on this system, but the other system is far apart. So, as I said, whatever I am doing on this system is not going to disturb the other system instantaneously. So therefore, if I can infer values of observable quantities of this system, doing it something here, okay, then quantum mechanics, you will see, tells you that you cannot do that. Okay, you cannot have sharp values of, incompatible observables. Okay. Right. So Einstein's argument, I'm not going into the details of Einstein's argument. Basically, I'm trying to give you the rough picture. So what Einstein did is doing something on this system, these two systems A and B. If A and B are correlated, doing something here is going to affect the measurement outcome of the B system instantaneously. And if I do two such measurements on A system, I can figure out the values of measured values of some measurable quantities of this other system. And quantum theory tells you that in general, observable quantities are incompatible. You cannot do joint measurement, simultaneous measurement of those quantities. Unlike in the case of a moving car, where you can figure out the speed as well as displacement of these things. Right. Right. So the question is then, what about quantum theory? Is it incomplete according to Einstein, or is there something else? So as I said in the beginning, we are not in a position to tell you whether quantum mechanics is incomplete or not, unless we specify some further properties. What we can tell you, and that is what John Bell showed, and later these people who got the Nobel Prize this year, they showed experimentally, that this idea of locality and realism or determinism together, which we call as local realism, is incompatible with quantum mechanics. So, quantum mechanical measurements on these two systems separately, the measurement statistics that it will provide you, will have inconsistencies with this principle of local realism, locality and determinism together. So this is what we are sure of. Okay. So actually, now it was 1935 then when Einstein, Podolsky and Rosen gave this argument that quantum theory is incomplete. 30 years, about 30 years were spent where people were discussing metaphysically, philosophically, etc. But no outcome, no definite outcome came out which can tell you that, look, I have this formula, I have this procedure. You go in lab and test whether quantum mechanics is incomplete or not. Test whether quantum mechanics is incompatible with local realism. So it was John Stuart Bell, was a particle physicist in CERN, who actually came up with this idea of statistical inequality, which we call as Bell's inequality, which Professor Mani has told you earlier. And this Bell's inequality, if one can go to a lab and do measurements on entangled system and figure out whether this inequality is violated or satisfied. If it is violated, then we are sure that quantum theory is incompatible with the notion of local realism. So there is indeterminism in quantum theory, but this indeterminism cannot be explained by the notion of local realism. Okay, good. So to make things shorter, so after this, so John Bell gave this, this Bell's inequality in 1964, although the paper was published slightly later. This is an obscure journal, it's called Physics, volume 1 it was published. So after John Bell, this is 64, people started, now John Bell gave this Bell's inequality looking into measurement correlation of a specific state, which we call as singlet state. I'll come to that. Later on, in 1969, Clauser, Horne, Shimoni and Holt, they came up with a much general inequality, statistical inequality, which does not, take into account only the correlations in singlet state, any state of these two photons, polarization. And nowadays, we call such inequality as Bell CH-SH inequality. And inequality, Bell-Sage inequality, has a broader perspective from the experimentalist point of view, because in experiment you cannot figure out that everything is very sharp, everything is very correct. There will be errors in experiment. So this inequality can take into account all those errors. So, so the inequality that we will talk about is this Bell-Sage inequality. Now thereafter, in 1972, the first experimental violation of this Bell-Sage inequality was done by Friedman and Clauser. Friedman was a PhD student of Clauser. And every such Bell experiment, the important thing is producing this entangled state of, in this case, 2 photons. Okay. Now there was, of course, it was very challenging, as Professor Mani mentioned, because we have just 2 photons. Think of it, this light, this light has plenty of photons. Billions. And if you want to have a photo detector which can detect a single photon at a time, is much, much, much difficult. Okay? But still, we are developing that. We are at a stage where we can have detector which can detect a single photon with a very, very high accuracy. Okay? Right, even more than 90% accuracy. Okay. But at that time, 1972, things were not so easy technically. Okay. So, then it was Alain Aspect and his collaborators who in 1980, actually they started from 1981, they started doing series of experiments for testing violation of Bell inequality with these 2 photon polarized states, and they developed much sophisticated experiment, and which can take into account some loopholes. I'll talk about these loopholes. This is called locality loophole. So this Alain Aspect's experiment was, it could take into account this locality loophole. Then Anton Zeilinger and his collaborators, what they did, Zeilinger is somebody, if you go to his homepage, you will see that all sorts of experiment in quantum foundations and information, which is possible or will be possible using photons, that he can manage. However difficult it is. Okay. So, this Zeilinger and his collaborators, they use these entangled photons for what is known as quantum teleportation, for experimental, verification of. So the first experimental verification of quantum teleportation, that means, sending information of quantum mechanical states of quantum mechanical system from one place to another place. Okay? Arbitrary state of a quantum mechanical system, and that was done experimentally verified first by Zeilinger. Later on, Zeilinger also did this Bell inequality violation experiment. In fact, the latest one in 2018, what he and his collaborators have done is excellent. He talks about all loophole free basically. All these loopholes what we will talk about, he came up with experiment which can get rid of all this. And this is much, much sophisticated experiment. Okay, so what I'll do, I'll not go through all these details.
Okay?
Okay. So now, in order to make you understand some of these issues, Professor Mani has already told, but I'll have to introduce little bit, not much, little bit about basics of quantum physics. We don't generally talk about basics of classical physics. We are all familiar with it. Even if we don't know the laws exactly, we are all familiar. Newton, yes. So, if I think of a coin tossing, so coin has head or tail, these 2 faces. Nobody can tell that, well, it can be something in between, half head, half tail. Can you have a coin like that? Unfortunately. Like a cat. A cat can be alive or dead. Can there be a state of cat which is in between? So, in quantum theory, this is not the case. In quantum theory, you can have like horizontal polarization of light or a photon, horizontal polarization of a photon and vertical polarization of a photon. Vertical polarization of a photon, which are orthogonal, which are perpendicular, which are distinguishable perfectly, but you can also have something in between. That means polarization along 45 degree, polarization along 135 degree, linearly polarized, circularly polarized, the superpositions of all these are possible. So, when I say in quantum theory, in classical world, any two states, like whether it is head or tail, whether the car is moving or it is static, every such thing are distinguishable. In quantum world, this is not the case. So, unfortunately, I have to use this Dirac notation, but forget about it. Think of it just a vector. So, I can have horizontally polarized photon or vertically polarized photon, which are perfectly distinguishable. Or you can have also linear superposition of these two. This is a normalized, so the coefficient mod square, these plus these will be equal to 1. So, this is a state of a photon polarization, which is linear superposition of horizontal. If you measure what is the polarization, is it horizontal or vertical, you will get with probability cos square theta by 2 it is horizontal, with probability sin square theta by 2 it is vertical, unlike in the classical world. In classical world, if I toss a coin, after looking at the outcome, I will say definitely it is head. I will say definitely it is tail, nothing in between. Okay, good. So, polarized light, I will not go through this thing. So, basically, we will use how to polarize a light. Because this light, what is coming from here or from this, so these are not polarized. Not polarized means it has infinitely many polarizations, mixture of all these polarizations. Okay, but so polarization means the electric field and the magnetic field, there is a particular direction here in the plane of wave. Okay. So when light passes to something called Polaroid, say kind of crystal, it have a definite direction, which is this polarization direction. So you can basically prepare polarized light. So if it is a like horizontal polarized, you can prepare a vertically polarized light or some other polarized light by something what is known as wave plates, quarter wave plates, half wave plates, concatenation of that it will. Okay, good. And when we talk about a composite system like a two photon or two spins, their states like if we have two coins, if I toss them independently, I'll have head, 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 tail, tail, head, or tail, tail, and all of them are these. In the case of two photon polarization, I can have all these states, HH, HV, VH, VV, but also their linear superposition. And this state is not distinguishable from HH. Okay, good. So this is all about the states that we talked about. I told you single photon polarization, how to prepare. There are different ways. You can use a particular polarized light and then use this quarter wave plate, half wave plate to prepare another polarized. For two photon polarized entangled state, so the first experiment was done when you take some calcium atom and then heat it up to a particular level so that it will release some photon. It will come to, so this is an excited state, total angular momentum 0. It will come to a lower energy level state with total angular momentum 1, and then again it will release photon to come down at the ground state with total angular momentum j equals 0. So these two processes, release of a photon mu1 and release of a photon mu2 can happen almost simultaneously, and they are kind of correlated. And this is how you can prepare a two photon polarized coelectric state, and this is what is known as preparing two photon polarized state using atomic cascade. So this is the cascade, and this is the process which Clauser and his student used, as well as Alan Aspect and his collaborator used for testing Thales Nobel. More modern version is what Professor Moon said, is the spontaneous parametric down conversion. So you have a laser light, which you call pump light, like this light. Here is a crystal, which you call nonlinear crystal, nonlinear in the sense that it will change the polarization of light nonlinearly. And then what happens is occasionally, this is very, very rare phenomenon, that you will have two such beams with particular, these beams mean with particular, wave vector, this is particular wave vector. So that the sum of this wave vector is same as the wave vector of the input light, and energy, sum of energies of this wave vector is same as the energy of the input light. So this conservation is there. And then this is called signal light, this is called idle light, such that this is correlated in the sense that if you put a photodetector, get a photon here, you will get a photon here. If you get two photons here, you will get two photons here. And this situation is such that getting a single photon here and a single photon here is most probabilistic compared to other situations. Although this itself can happen very, very rarely. But this is a process of preparing this two photon entangled state, polarized entangled state, and that is what we will use these days for several experiments, not just for Pellini. Okay, maybe I'll not go through this in vector notation, this is fine. I'll not go through this. And observables, as I said, you can measure position, you can measure momentum, you can measure polarization, etc. So Born rule tells you that if I measure, because quantum mechanical measurement is probabilistic, so if I measure an observable A, which may be position, momentum, spin, polarization, etc., and prepare this system in this state vector psi, it will provide one of the outcomes, and this one of the outcomes are eigenvalues of this observable. So this is slightly mathematical. This observable means is a matrix which is Hermitian. If you take dagger or adjoint, it will be the same. Its eigenvalues are real, and eigenvectors are also orthogonal. So the ith eigenvalue will occur with this probability. So this is the overlap of these two vectors, psi I and psi 1 square. And after the measurement, the system will jump or collapse into this corresponding eigenstation. So this is what we understand by quantum. Unlike in classical world, this collapse happens. And there is a big problem which is called measurement problem, is how these collapse happen. We don't know. Okay, so measurement on single system, as I said, this is the probability, and measurement on a combined system or entangled system, this is the entangled state which is called singlet state. So this is HB minus BH. H is the correct. So when the A photon is horizontally polarized, B photon is vertically polarized, or when A photon is vertically polarized, B photon is horizontally polarized. This is the superposition of these two. Okay. So if I measure, if I measure on the A photon, whether it is horizontally polarized or vertically polarized, if I get to see it is horizontally polarized, then the state, joint state of A and B photons is HB. If I get to see B, the A photon in B state, then the joint state of A and B will be BH. Okay. So, and this is happening with probability half because not square all this will be. And we say that this state psi minus is entangled because it cannot be written in this form. In the sense that I cannot assign a state vector to A photon and the state vector to B photon when this is entangled. Right. And well, I'll skip that to basically how to measure this polarization. That is fine. And another way, mathematically same, is what is known as Tangala. So if you have electron which are spin, if you send like an atom, like silver atom, to this magnet, where north pole is there, south pole is there, and this is the magnetic field, inhomogeneous magnetic field along this direction, then unlike in the classical case, classically you will get the detection of the the atoms everywhere, some distribution, but in the quantum case we have this spot and this spot on the field. So that makes the difference in the classical. So I have already given this argument of Einstein, Podolsky and Rosen. I'll not go through that. What basic thing is that Einstein said that look, by doing something, two measurements on my system here, I can figure out the values of two observable quantities on the other system without actually disturbing the other system. And quantum theory tells you that such observables like spin measurement along z direction and spin measurement along y direction, these are non-commutative. You cannot measure them jointly, simultaneously. You cannot have sharp values of spin along y direction and along y direction simultaneously. Therefore, these, so Einstein said that look, a complete theory should have all values, but here is a situation where on the B system I cannot have all values. Therefore, quantum theory must be. Right. So I'll skip this thing. So Bell's inequality, as I said, is, so what John Bell did is that, look, I will just stick to this local reality principle, local realism principle, and see what a physical theory tells us. What kind of inequality, statistical inequality we can do. So for that, what he did is, so he used something called local hidden variable. So this local realism is that if I do something here, it is not going to affect the other systems instantaneously, and if I perform measurement on my system, it will only reveal those values, nothing else. So using this local hidden variable means that these two systems A and B, let's say two photons polarization, they have an underlying connection which may not be material connection. They have an underlying connection which I call as lambda, so that based on the values of lambda, I can determine with certainty what will be the measurement outcome of some observable for A system, what will be the measurement outcome of some observable for B system. Okay, so that is the idea of local hidden variable. So it says, and this hidden variable can have, hidden means, like in point of saying, I don't know the force, I don't know the speed, initial speed, I don't know the air resistance. So if you put them together, it is called hidden. And why hidden? Because experimentally I cannot figure out what exactly value of this variable is. So what Bell did is that using this notion of local hidden variable, he came up with this correlation. So the value of some observable VA can be plus or minus, VB can be plus or minus. It depends upon the observable A and this hidden variable. And then if the hidden variable itself can be probabilistic, it can have probability values. And then you take the average, which is here integration, which is the experimental joint correlation. And Bell inequality tells you that if on A side, if I perform measurement of this curly A or curly A prime, and on B side, if I perform measurement of curly B and curly B prime or curly B prime, then this inequality, magnitude of this thing, CAB plus CAB prime plus CA prime B minus CA prime B prime, magnitude of this must be less than equal to a local hidden variable. Okay, so this is what is known as Bell's CHS. Bell's inequality, Bell's original version is not exactly this, as I said, this is okay. And then what Bell did is that for the singular state, what I mentioned to you, this 1 by root 2 HB minus VH, if you take that and if you perform measurement of some observable like AA prime, and these are basically observable is sigma dot J. So sigma x, sigma y, sigma z, these are the components of sigma vector, and J is the unit vector in 3 dimension. Well, what he showed is that this quantity, this correlation, QM means quantum mechanics. This can have value, maximum value, which is of course greater than 2. Therefore, we have a violation of Bell's CHS inequality in quantum. So, now, is it the end of the story? One story is finished. What is that story? It tells you, Bell's inequality tells you that quantum theory has contradiction with local realism. So, whether quantum theory, Einstein was happy with quantum theory or not, from the perspective of local realism, finished, dotted. So what is it that we'll have to figure out? We'll have to figure out, well, one might say that who cares whether quantum theory is incompatible with local realism or not? Who said that quantum theory is proper description of nature? So we'll have to figure out from experiment that whether nature satisfies this local realism. Whether correlations in nature, in experiment, nature means when experiment we do, whether that is compatible or incompatible with one. That is what we have to do. So the experiment is for justifying local realism in nature, not for quantum theory. Quantum theory, it has been established. Okay. Right. Okay. So this is the the directions of measurement. I will read this. So let me just mention briefly, because I am not an experimentalist, we don't have time also, that what sort of experiment people have done for this taking of Bell inequality. So idea is that you have this source S which produces these entangled photons. For example, one photon goes to this polarizer where you measure the polarization. Another photon goes to the left side for doing measurement of polarization. You can do polarization measurement along some direction, and you have these two outcomes, whether it is horizontal polarized, vertical polarized or negative, or whether it is 45 dB polarized or 135 dB polarized. Similarly here. So you can have this x, y, z. So x is this, z is this, and perpendicular to this plane is y axis. This is the general scheme. So the first experiment by Friedman and Clauser, they use this atom calcium Oman, so which it has basically Oman. These are the atoms, and then you have a laser light, purple light, which is thrown on this atomic beam, and then for excitation it will produce these two photon states. One photon will go through this polarizer and then measurement. Another photon will go through this and then measurement. Okay, and then you have a coincidence count. Coincidence because you want to see whether two photons are together or not. Now, this gave rise to violation of Bell inequality, but it is, beyond it. Oh, it is beyond any doubt. It is not beyond any doubt. There are too many loopholes there. Okay, so as I said, drawbacks of this experiment: paths of the two output photons from atomic cascade do not have specific. So these are not specific paths. We have said this thing, but basically this is very broad light. Here also very broad light. So even if you put detectors like here, it doesn't matter. You cannot count everything. Photomultipliers, that means these photo detectors, these are not good detectors. And third, which is very important, is that we'll have to justify that once the paired photons is created here, only after that you are performing measurement. If you do the measurement beforehand, then it is something else. So this is what is known as locality loophole. So this experiment is, it cannot avoid the locality loophole. Okay. So if you want to, if you are slightly familiar with the special theory of relativity, you see that this is the position and this is the time axis. So if you have entangled photon which is created in the past, and the measurement that you are performing on Alice's side and Bob's side, this event should come beforehand, before the light comes, so that this creation of this photon to pair photon will not affect the choice of measurement. But the outcome can happen here. Okay, so this is basically the idea that was used by Alain Aspect, and he used same thing, these atomic cascade, with a modified thing, so that they use some laser beam to create these photons, entangled photons, and then this coincidence count. But the distance between these two detectors from the source to photon source is such that it invariably satisfies the locality. That means this locality loophole in his experiment is not there. So the distance is, I think it is 10 meters or something like that, so that problem will not be there. But still, the problem is with the detection. Photo detectors are very bad. At that time, it was maybe 20%, 30% efficiency were there. Okay? And whenever you have all these problems, you cannot claim with certainty that Bell inequality is violated. Okay. So then, good source, which is called spontaneous parametric down conversion, came, and then in spontaneous parametric down conversion, the problem, the thing is that even though it is a rare phenomena, still we know that whenever two photons are created, they have definite paths. So we don't have any problem in that. Okay, and people have used that also, like Mandel and his co-workers used it for Bell inequality violation. Now the question of loopholes. So what happened is that there is this locality loophole I mentioned. There is also detection loophole. That means your detectors are not perfect. Question is, can we design a Bell inequality violation experiment which can take care of both these locality loopholes and detection loophole, so that you will not have any of these two loopholes. And this was very challenging. Why? Because the experiment was done with photons. Photons don't interact, so it can pass through a large distance, but detection is very bad. Okay? On the other hand, if you take matter system like electron spin, etc., it cannot propagate a larger distance without affecting its entanglement. But the detectors are very good. So you will have to do something in between. And that is what a group did with this Roland Hansen in Delft University. What they did is what is known as entanglement swapping, where they use these two NV centers nitrogen vacancy bond in diamonds, and the electrons are they have correlation with photons. I perform measurement on these two photons so that these two electron spins they become entangled, and then you can do the Bell test there. The other experiment was done by Anton Zeilinger's group in Austria and this NIST Boulder group. So all these three have been done in 2015 to get rid of both these loopholes, and recently in 2018, Zeilinger and his collaborators. So locality loophole, detection loophole, done. I mean, we can say that these two loopholes are not there. There is one more loophole which is more philosophical in nature. What does it say? There are two systems, Alice and Bob. I mean, two spins in two labs. I'll have to choose measurement, one of the two measurements on my system, one of the two measurements on his system. I mean, he will choose. Question is, this choice should be, in Bell inequality experiment, this choice should be at random. How will you decide that they have chosen it randomly? Number one. Number two, how will you decide that choice of one measurement and choice of other measurement, they did not have any common past. They don't have any common past. Okay? So how will you do that? So what people in physics, we generally take it to be, we take it to be granted is that what is called free will. So what measurement I will do on my system, it depends entirely on me, not on a far apart system. So this free will is a kind of philosophical issue, but what Zeilinger and his collaborators did is that the choice of measurement on one lab, he connected it with a cosmological event which happened, let's say, at the time of Big Bang. Okay? So that there won't be any connection there. And there also he figured out violation of this Bell inequality. So now we are in a position to say that yes, we have actually full proof of Bell inequality violation. So nature also does not satisfy in general this idea of local realism. Now you might say that, what is big deal? Let nature behave like this. Well, the thing is that this experimental verification of Bell inequality violation has consequences. What are the consequences? Is that the security of quantum key distribution, the perfect randomness or certification of randomness of some events, or certifying some measuring quantities using this quantum technology, it is based upon the Bell inequality violation. So once you can certify Bell inequality violation, you can certify several things, and those are all the technological aspects which people are working on, and hopefully in near future we'll get to see those technological advancement in our real life. Thank you.
I must tell, it's a very difficult subject. Okay, let me actually confess. Now, it cannot be done in 1 hour. Okay, what he has given is a introductory part of it. Now, basic question is nature, the laws of nature, deterministic or not deterministic? Now, we all know, and we have been using determinism, because we know sun rises every day morning, right? I can predict when it will come in the sky. We know when the eclipse will take place. That is determinism. In fact, we know for the next 1,000 years when the eclipse will take place, which place it will take place, also we know it to a very large extent. Okay? So there is determinism as given by Newton's laws of motion. The basis is what was given by Newton 400 years before. Now, is the determinism or laws of motion as given by Newton, is it valid at atomic and lower scales which are there? That is the fundamental question. It raises extraordinary situations, and we had to revise, change. Now, as he mentioned, Einstein, being a believer in determinism, he said, yes, there is probability because of our inaccuracies in measurement, etc., but the underlying theory is deterministic. That is the point. But when we do the measurements, quantum theory as given by Schrodinger, Heisenberg, etc., proved to be extremely successful. It is successful because you can measure the spectrum, hydrogen spectrum. We know even what is happening inside the sun, from the even stars, because from the spectrum itself we know what is the temperature, what are the materials inside, what gas is there. All those things we know. Okay? But so quantum theory plays a role in precisely telling you what is happening there. Now, the question which Einstein asked was, is it still, because the interpretation is probabilistic, is the underlying theory probabilistic or is it deterministic? That is the question which was bothering him. So, in order to circumvent all these things, they created something called hidden variable theory. Essentially, okay, these are the things, but there is something more which we don't know. Since we don't know what are those things, we will average out. Whatever unknown variable is there, we will assume probability for that. As he said, I can in principle find out if I toss a coin, if I know the initial velocity, if I know all those things precisely, exactly, I can tell you classically whether you will get head or tail. Okay? But we don't know. So all those unknown informations, you put it as some variable and then call it hidden variable theory, etc. So quantum mechanics, quantum theory, can I be explained? The indeterminism which you find agreeing with Schrodinger's equation, etc., can it be explained by this kind of a mechanism? And what was Bell and others proved was that kind of hidden variable theory is incompatible with local realism. That is all the basic question. And now the Bell's inequalities are verified. That is and it leads to certain new things, not only at the fundamental level of theory, in terms of applications. The quantum technologies, can I communicate, can I give information, etc. So the earlier questions were, well, all of us are dependent on money transactions through internet, etc. You will always wonder, can somebody hack in between, right? Can somebody collect that information and collect my data and take all my money out? That is the point. So the current system within the classical computer is that it is difficult, impossible. It is practically impossible to hack because they have created a cryptography, some kind of a codes which will be very difficult to do that. Okay, that is what is the basic idea. Now with the quantum thing we can do that, but there are more problems with that also. So there are a lot of interesting things in the last couple of decades which has gone from speculative, philosophical and other things to actual experimentation and technically finding out results. So this is the status as of now. Now, as many college students have come, I would urge you, several people Science Forum know from IIT Madras, from our place, etc., who are reasonably well versed in what is happening in the aspects, well, Alan Aspect's work, and also what is the basis on which the Nobel Prizes have been given. So if you want any help in organizing in your own college, okay, program, if you contact us, we will provide appropriate links so that you can have little more discussion, more focused discussion, better understanding in your own places of institutions, so that other students, everyone will be benefited. So I'm going to stop it here. Okay? So now we are going to start. We have in fact quite a bit of time. So we are going to start question answer sessions. So all of you, there are a lot of you who would like to ask questions. Okay? So you should ask. Don't hesitate to ask. We'll go for at least half an hour to 45 minutes.
The first question we'll call from the internet. This
Okay,
Zoom meeting question.
Okay, already some question has come. Can you read it?
Yeah.
Yeah, may I know what is the entangled state, sir?
Okay, go ahead.
So as I said, entangled states are states of a composite quantum mechanical system, like a system of two photons polarized when I take polarization degree of freedom. And it is a state such that we cannot assign a state vector to individual photon polarization. So that is what is known as entangled state.
One more question from Zoom participant. Is the beta or kind of a decay from a nucleus is just because of presence of loophole in nucleus? Beta decay.
No, what is the question?
Is the beta or any kind of decay from a nucleus is the just because of presence of loophole in nucleus?
Just because.
No, there's nothing to do with that. So this alpha decay or beta decay in nucleus is due to a probability behavior of quantum theory which is happening. Okay, alpha particle come out of nucleus even though it does not have that energy. Okay, there is a decay which is taking place and nothing to do with the issues about loopholes, etc. It's a probability of the quantum theory which is always playing that role.
So anyone want to raise any question? Please raise your hand.
Please raise your hand and then we'll go ahead and ask. Okay. Here. Please identify yourself.
Sir, you can sit there.
So my question is, in quantum cryptography, we will set an algorithm for the spins of clockwise or anti-clockwise using the binaries. We will transfer the data for the quantum using the cryptography.
Okay. So what is your question?
So my question is, can we set the algorithm for the quantum cryptography using the binaries?
Well, quantum cryptography, I'm not sure how familiar are you. So there are different ways of design. So cryptography, is basically sending information in a secured manner.
Okay, sir.
Okay, and the scheme that people use in quantum cryptography is called one-time pad. So you have your message which you can express in terms of binary string as we do in the computer, classical computer. You have a binary string that means 0, 1, 0, 1, 1, 0, etc., etc. And then you add another binary string which is fixed, which is with me as well as with you. If I am the sender, you are the receiver. I add them, with binary addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, something like that, binary addition. And then the resulting bit string, I'll send it to you. What you will do, you will add your same bit string, which is key, you will get the same message. Okay, this is what is known as one-time pad. So in classical world, the sharing this key, which is called private key, is a difficult matter because any intercept can figure out in principle what is the shared key, whatever be the intelligent way by which you are sharing the key. In quantum world, sharing this key happens using fundamental laws of quantum mechanics, which tells you that two non-orthogonal states cannot be distinguished exactly. Or in other words, you cannot clone, make 2 copies or 3 copies of arbitrary quantum mechanical state. So if you take like photon polarization, horizontal, vertical, 45 degree, 135 degree, send any such polarized photon to the receiver. Receiver can perform measurement in horizontal, vertical or 45 degree, 135 degree to figure out the way it has been, in which basis it was prepared, and accordingly they will share the key. Okay, this is the way it is done. And here, this question of eavesdropper getting hold of the message will not happen. Okay, yeah.
Thank you, sir.
I just want to mention, see in classical this thing, supposing your name is Raj, okay, R-A-J. Now you want to send that information, that person will come to another person. Now obviously if you say somebody, some person can catch hold of that Raj and take him and do whatever they like. So in order to do that, we will say no, it is not R-A-J. For every letter R, I will put 3 letters from there. Instead of R, okay, A, B, C, D, okay, P, Q, R, S, T, U. Okay, you put those 3 letters, every 3 letters. So that is a trick which adopt, a code which we adopt, or crypt which you use, and that is what is done. From there, the person who is in between caught, he will get something like UCF, something like that he will get. Oh, who is this? I don't even know who that name is. Unless he knows the trick, from there I have to go back and get that. Okay, so that is done classically. In quantum thing is that addition which is done is controlled by quantum mechanics itself. It's not a classical thing alone. So that's what helps you in quantum cryptography, and of course it's all tied up with the same thing. Okay, sorry.
Sir, regarding locality loophole and detection loop, isn't that isn't that sound similar to Heisenberg uncertainty principle and Lewis where we start?
Why do you think so?
Because I feel that sounds similar to that.
No. Locality loophole tells you that I perform measurement on my system and the measurement outcome, okay, so the act of measurement on my system should not affect the measurement outcome on a distant system instantaneously. How will you guarantee that? So in experiment theory it is fine. If I do it in the the light cone or something, we can do that. Question is, in experiment, how will you guarantee that? So you will have to set up the detectors at 2 labs far apart, so that it will guarantee that when detection happens in one lab, it is not going to affect the measurement outcome in the other lab. So it has nothing to do with Heisenberg thing. This is true in classical world also. Okay, and detection loophole, it has again nothing to do with Heisenberg thing. See, for photons, because they don't interact much, detecting them is, so how do we detect photon? I mean, that 1 photon, 2 photon, etc. Photon comes in a detector, you use a diode, for example, so it will excite lots of electrons. Those electrons will again excite even larger class of electrons, and then it's a motion of electron that will produce the charge, the current basically. So you detect that. Okay, so this is how we know, basically this is the photon multiplication. Question is, photons, because they don't interact, detecting them also is very difficult. So you don't have better efficiency, much efficiency. So it has nothing to do with Heisenberg principle.
Thanks.
Can you read?
Is entanglement depends on time.
Okay, so whatever we discussed so far is about a underlying space-time is non-relativistic. Okay, if you take a relativistic space-time where position and time, I mean displacement and time, they have same status, where Einstein's theory of relativity holds good, there even if I prepare a joint system in entangled state and these 2 subsystems travel, if there is acceleration in the motion of the subsystem, then the amount of entanglement can get affected, and thereby the So basically with respect to time, it can affect the entanglement. So this is in the relativistic scenario. Even in the non-relativistic case, because quantum systems are very, very prone to interaction with its environment. So even if I prepare two photon in polarized entangled state, they will not remain in that entangled state for a longer time. So it will decay. With respect to time, actual world, it will decay.
Okay, go ahead.
From Banu Natraj, is teleportation is same as quantum entanglement?
No. So one can show that, in fact, theoretically one can show that in order to have quantum teleportation, this is in quotation. Quantum means, it is not, you are not using just classical resource. If you use quantum resource, if you want to have quantum teleportation, then entanglement is necessary between sender and receiver. But even if entanglement is there, you may not have quantum teleportation. So these two are not synonymous.
Yeah, one more question. Is there a possible that entangled particles are no longer a different particle, but same particle in different space?
Okay. So, entanglement is something which is physical in the sense that we can perform measurement on these two particles or modes whatsoever and figure out whether they are entangled or not, and one can identify properties of individual particles by performing measurement. So therefore it is not true that entanglement means of two particles means they are same particle. Well, the question is slightly different when you take system of indistinguishable particles where you have boson, fermions, etc. So there the question is much more difficult. I am not going into that detail. So far we discussed only about distinguishable particles, although photons is not distinguishable when you put photons in one place, but that's a different issue. But the point is that when you take distinguishable particles entanglement of distinguishable particles, then these, you cannot say that entanglement between two particles means it's one particle. No.
Yeah, couple of announcements from the organizers. Before you leave, please send your feedback. We have provided the feedback form at the entrance, and please fill up the feedback form and hand it over to us. This will help us to improve our future programs. We also have the form to become the member of Tamil Nadu Science Forum. That's also available. The annual subscription is 30. Those who are interested to become a member of Tamil Nadu Science Forum, please become a member. And we also place some of our publications, science publications and science magazines, Tulir and Jantar Mantar. You can subscribe the Jantar Mantar. Jantar Mantar is in English and Tulir is in Tamil. So we have two science magazines publishing from the headquarters. Please, those who want to subscribe, you can do that here. So that's the announcement I want to make.
Okay. Questions?
Sir, my name is Bhuvan, sir. I am studying in Government Arts College in Nandam, Chennai. Sir, my question is, what struggle solving for theory of everything, sir? Struggling solving for theory.
What struggles?
Theory of everything, sir. So why cannot solve it, sir?
Everything. Okay.
But unfortunately, an attempt like that will be too complicated because the universe is too complicated. So theory of everything, it's only for philosophical or science fiction.
I would say we are not in a position still now to either to deny or accept whether theory of everything will be there or not. No.
But even that we don't know.
Yeah.
Okay. Okay.
Hi, my name is Jatin. I'm from IMSC. I had a question that these entangled particles, at what length scale these entanglement gets vanished away? Like there may be a scale, and what would be the reason for it?
Okay. So as I said, even in the case of your background space-time is non-relativistic. That's what we discussed here. Quantum systems are very much prone, as you know, to interaction with its environment. So if you take photons, there will be carriers. Photon polarization will be with some photon, and then this photon, maybe polarization degree of freedom or other degree of freedom, like orbital angular momentum degree of freedom or something, will interact with something else. So therefore, because of this, so the lifetime of each such system is very small compared to classical system. Therefore, whenever you produce entanglement, its lifetime is small. I mean, we want to have entanglement with higher lifetime, but this is small. The question is the length scale. So length scale, of course, it depends upon what sort of interaction you are having. If you are dealing with photon, this is not a problem. You can have two photon polarized entanglement at long distance. But if you have electron spin, of course, that is a problem. So it depends upon what physical system you are talking about.
Sir, I'm Ritesh, and my doubt is that Ritesh from Pondicherry University. Sir, my doubt is that we know that two particles are entangled, okay? Let's say the two are entangled. We take one particle to one end of the universe and other to other end of the universe. So they're correlated. We do a measurement, okay? So when we do a measurement, one will affect the other. So doesn't mean that information passage, doesn't it violate the relativity principle?
No.
So that is my doubt, yes.
Okay. So the point is that yes, it is true that the instantaneous collapse of state happens on the other system when I do something here. But this instantaneous collapse cannot be used to send physical information instantaneously. So to send physical information, you will have to take the time, like speed of information, like the speed of light, etc. You cannot do better than that.
There are other questions? Yes.
I should not ask, but yeah. So is entanglement done only between particles that have two states, or can they have multiple states?
No. I mean, entanglement, as I said, with photon polarization, the singlet state, as I mentioned, so you can express the singlet state in terms of horizontal vertical polarization. You can express it in terms of some other linear polarization like 45 degree, 135 degree. You can express it in terms of circular, right circular, left circular. So it is up to you. So this is the important thing, that when I do measurement in classical world, I can figure out a finitely many, or which is called granular outcomes. So whether it is head or tail, whether it is up or down, something like that. In quantum system, when I talk about measurement of polarization, it can be horizontal vertical, it can be 45 degree, 135 degree, it can be anything in between. So you can have continuous outcome by setting up your measurements, which is not possible in the classical world. So the granularity of measurement is there in classical world, but this continuum of granularity is absent in classical world of measurement.
I just want to add one more. For entanglement of positions are possible, or momentum.
In principle possible, yes.
So how could we know if two particles are entangled regardless state of one particle is affected on another?
Can you repeat the question?
Yeah, I was asking that how could we know if two particles are entangled regardless the state of the one particle is affected on the other particle? Like two particles are separated, right?
See, the state affecting other is, question is when I can affect some system by probing the system, by performing measurement on the system, okay, or doing some operation, maybe rotation, translation, etc. Unless you probe a state affecting other system, it doesn't make sense physically. So maybe you have something else in your mind.
Like I'm asking that. How do you know if two particles are entangled?
Okay. So So how do you know two bodies are entangled or not, right? Okay. So there are different ways of doing that. One way I told you is the violation of Bell inequality. So you have two photon polarization. You perform measurement of photon polarization. Horizontal, vertical, 135 degree, 45 degree, 135 degree, 45 degree. Look at the Bell inequality, see whether it is violated. If it is violated, you are sure it is entangled state.
Is there any other means for doing
there are
that?
other means, which is called, detection of entanglement, entanglement witness, etc. There are so many other things of doing that. If Bell's inequality is violated, then it is entangled. So,
Can I just add here? See, the Bell's inequality which was written here there are many correlations. When you actually do an experiment and calculate that, if it is more than 2, the value, then it is certainly entangled. Depends on how much more. It can go up to 2 times root 2. And that's the maximum entanglement. But if it is less than 2, you cannot say whether it is entangled or not. There are more tests required for that. Again, a large amount of research work has done on how do you measure entanglement. How do I know this entangled state is more than the other entangled states? These are part of it.
So entanglement happens even at less than 2 as well.
Yes, possible. Yes.
Oh, you want to ask?
Sir, how to observe the spins of the entangled particles?
So you just apply the Stern-Gerlach and figure out the spin. Yeah, Stern-Gerlach experiment. You do that.
Is there any other question? Okay. Okay, last question.
It's kind of a weird question to ask, but what I want to ask is, can two different entangled states be entangled with each other?
And different entangled states be entangled with each other. Okay. So this is a mathematical question you are asking. Yes, it is possible mathematically. If I have, let's say, 3 particles, okay, then I can have, say, A, B, C. I can have entangled state between A and B. I can have entangled state between B and C. It is possible. I can may also have entanglement between A and C. That is also possible. But there is something called monogamy of entanglement, which says that if I increase the entanglement between A and B, entanglement between A and C will decrease. Okay, something like that.
Okay, thank you very much. We have to wind up now. One minute. There are a couple of things. You want to give any specific reference or anything? Popular reference?
Okay, so actually there is this book by well, there are many references. I would say that there are some review articles by Alan Aspect. Okay.
YouTube also.
YouTube also there. So you can figure out those. I mean, several such review articles are there. You can look into it. Alan Aspect is although an experimentalist, but is a very, very good expositor of theory.
Okay. Okay. You want to say something?
No, I just want to show this book.
There is a book which Professor Mani is recommending, When Quantum Physics Was Reborn, The Age of Entanglement by Louisa Gilder. Okay? You may want to have a look at it. It should, I don't know, many colleges and other places may have the copy. And, okay, Murugan, you go ahead. You want the mic?
For the students here, I think it will be helpful to the students. That's what I thought. Professor G. Venkataraman has written a series of books, about a dozen of books on vignettes in physics. All of them are aimed at BS. It is aimed at plus 2 level, but it will be more plus. It will not be at plus 2 level. It will be around basic level. As third book on what is reality, it is exclusively devoted to EPR paradox and then Bell's inequality. And surprisingly, it's not a popular book, it's a semi-popular, technical. Surprisingly, it also gives a very good description about Allen aspect of the class experiment here, with the full details including here. I thought I should just tell for the sake of students.
Thank you very much. So, we will now wind up. Shubhashri, who is our TNS of PSL main person now, doing a lot of work, she will propose a vote of thanks.
Thank you, TRG. So thank you all for coming here. It was a great pleasure to organize this session. It was enthusiastically, first of all, I've just recently joined Science Forum, so I can say the enthusiasm of the Science Forum people for organizing these lectures is really immense. Thank you, Professor Mani and Professor Sibashish, both of whom agreed very immediately. As soon as we approached them, they agreed with so much enthusiasm, and it was such a wonderful thing to do. And we would like to thank the hall, for the hall, we would like to thank the Anna Centenary Library people. It's a very wonderful location for all of us to gather and discuss, except that they leave your bags outside, so now we have to go collect the bags. Thank you, TRG, for moderating it. And yes.
Okay, thank you very much. Now, the certificates for the college students will be available. Okay. Okay, thank you very much. Thank you very much for all the help you have. And in fact, I'm very impressed. A lot of students stayed till the end.